Okay, so we're ready for the last session of today. So as I told you, Monday, John Ross unfortunately has to go back to DC for medical reasons. Fortunately, John is doing well, as you can see. So he's joined us by Zoom from DC, and he was going to then give the final lecture on the connection between machine learning and structural estimation. And I think this is going to be a joint lecture with Enoch Kang, is that from Washington University. So, John, the floor is yours. Thank you very much.
Thank you, Dennis. Yes, I'm really sorry I can't be there. I was supposed to come to Copenhagen a week ago, and my wife and I, we got hit by a truck. We're both okay, but it was a little scary, and my heart got knocked into an arrhythmia, and I have to have an electrical shock. It's called a cardioversion to get it back into normal rhythm. So. Just staying close to home, but I'm doing okay. I'm not going to have a heart attack or anything. But so I was supposed to be giving the lecture today. I understand it's very hot in the room. We'll try to not spend too much time. But even if I would have been there, I would have been. I invited Enoch Kang, who you can see in the screen, and he's got a very impressive paper that is combining dynamic discrete choice with ideas from reinforcement learning. And we'll also be talking about what we call model-free versus model-based. And the model will be the transition probability. And the question is can you be non-parametric in that dimension? And Enoch will show you how you can do that. But it happened that I was asked to write by the Oxford Research Encyclopedia on Economics and Finance, an article that draws the connections between structural estimation and reinforcement learning. And I've done that jointly with Pranjal Rawat, a student at Georgetown. He's going to be on the job market next year as well. He knows quite a bit about reinforcement learning. It's a very hot area. And so I'm just going to give you a brief overview before I go in to turn it over to Enoch. So let me see there we go. So in the Dropbox are a couple articles. One, they look like almost identical. So one is going to be a chapter in Pranjal's thesis. It's called Structural Econometrics and Reinforcement Learning. And then another one is for this Oxford handbook that focuses down on something even more specific. It's called inverse reinforcement learning. And inverse reinforcement learning has very strong parallels to dynamic structural estimation. It started around 2000. There's a famous article by Stuart Russell at University of California, Berkeley. He's kind of in the engineering AI. He has a famous textbook on artificial intelligence, and he introduced the concept of inverse reinforcement learning. So you can read that paper, and that's going to be the closest to what Enoch is going to be talking today. And we actually discuss Enoch's paper and also a paper that uses temporal difference learning, a paper forthcoming in Review of Economic Studies by Karun Abdusumili and Dita Eckhart. And so that's we won't be talking about that today. But let's just give an overview. So structural estimation, that's what we do. We don't need to explain that. And then you can think about machine learning, at least that's how I think about it, as it's a subfield of artificial intelligence that allows computer systems to learn from data, improve their performance without explicit programming. So I would think about the predominant example is deep neural networks that have been used to train large language models, do translation and all the amazing things you see doing on ChatGPT. Now, reinforcement learning, that's a subfield of machine learning where the agent learns to make decisions by interacting with an environment to maximize a cumulative reward via a trial and error learning by doing process, where the agent responds to rewards it receives while interacting with its environment, dynamically updating its actions to achieve optimal performance. So you might have heard of a predominant method of that. It's called Q-learning. It was introduced by a guy named Christopher Walkins in his thesis in 1989. And initially, it was motivated by animals that live in the environment and, they kill something and they get a reward. And they learn that if they, hunt in a pack, they can be more, they learn from experience and they learn strategies by learning by doing and gradually improve over time. But this has been taken into the computer realm, and I would say reinforcement learning, you should think about them as stochastic algorithms, iterative stochastic algorithms for solving dynamic programming, MDPs, Markov decision processes. And then finally, reinforcement learning is a subfield. Inverse reinforcement learning is trying to do exactly what we do, is using reinforcement learning as the algorithm, but trying to say, here's behavior, let's invert that behavior and try to infer the underlying reward function, that's what they are going to call the utility function, that generates that behavior. Now, so why do let's just talk about why we do a structural estimation and why we'll call it they do reinforcement, inverse reinforcement learning. Well, you've probably already heard that one of the key know that it's counterfactual predictions is why we do this. The idea is that it's just like in manufacturing a car, they used to crash cars, new car designs with real cars with crash dummies, and they found out they could build computerized finite element methods, models to do virtual crash tests. So it's much, more effective and faster to do, sufficiently realistic methods, crash test them on the computer than actually using the entire United States population to crash test a policy. So the other thing is that we're interested in the statistical properties of our estimators, like testing hypotheses and providing confidence bands. So we're interested in the theories of economics. Now, in terms of the reinforcement learning, why do they do it? They're not so much interested in the inference, I would say, as we are. They want to train robots and AI to behave intelligently like people. And and what's found is that in many cases that if you can uncover a reward function, it's a much more parsimonious way than doing what we would call reduced form estimation, which is estimating the CCP. In this literature, they call that behavioral cloning. That is like, as Victor and others have talked about, that choice probability can be very, very high dimension, and even in single agent problems. And in many cases, you can have a much more parsimonious reward function. If you can solve the MDP, you can generate the CCP and get very intelligent predictions of behavior much more parsimoniously. So the idea is that in many recent AI applications, you can see that using in reinforcement learning, generally the reward function is known. So an example would be using Q-learning to play chess. The AlphaZero is like very famous for learning how to play chess, and it was using this Q-learning algorithm. And but in playing chess, it was doing this by self-playing, playing copies of its algorithm against its own in a simulated environment on the computer. And the reason they were able to do that is because the reward function is pretty simple. It's 1 if you win, -1 if you lose, and 0 if you draw. So, but there's many other examples where the reinforcement learning is not so clear. So let's just look at this quote here. There's a paper called Deep Reinforcement Learning from Human Preferences in 2017. And he says, suppose we wanted to use reinforcement learning to train a robot to clean a table or scramble an egg. It's not clear how to construct a suitable reward function, which will need to be a function of the robot's sensors. In this work, we will explore goals in terms of non-expert human preferences between pairs of trajectory segments, essentially looking at what people do in practice. We show this approach can effectively solve complex reinforcement learning tasks without access to the reward function, including Atari games and simulated robot locomotion, while providing feedback on less than 1% of our agents' interactions with the environment. This reduces the cost of human oversight far enough that it can be practically applied to state-of-the-art RL systems. We showed that a small amount of feedback from non-expert human, ranging from 15 minutes to 5 hours, sufficed to learn both standard RL tasks and novel, hard-to-specify behaviors such as performing a backflip or driving with the flow of traffic. So these methods are actually being used, like for autonomous vehicles and other examples. Another paper that we have in the Dropbox is by Barnes et al. At Google, using inverse reinforcement learning to apply at Google Maps. And so here in Google Maps, they have this incredible data set of everyone choosing to go from A to B, origin to destination. And but they want to improve the maps to find out what's your preferences, right? So you might think about safety of the road, like we experienced on the expressway when we got hit, the time, how pretty it is, and so on. So there's all these trade-offs that humans make when they find a good destination. So what they do, it's in a pretty amazing paper using inverse reinforcement learning. They learn a reward model with 360 million parameters. And they show that using this reward model, they can improve Google Maps and generate a 16% to 20%, 24% increase in route accuracy relative to other baseline models. And a final application is aligning ChatGPT. You probably heard about ChatGPT doing these things like hallucinations or just giving inappropriate content. So ChatGPT is a humongous deep neural net transformer model with hundreds of billions, maybe up to latest versions, trillions of parameters. And so this paper by Ouyang called Instructed GPT showed that the initial training just is, it's a token predictor. It's predicting words. So the objective function is to try to, you think about it as a nonlinear regression, very many parameters, very flexible, that predicts tokens. But when the output of that, some of these outputs, and they're probabilistic, you can think of them almost as a dynamic discrete choice model, and some generate better answers than others, and there's a certain probabilistic outcome. So you can play, you can give prompts and answers, and so initially they would hire human beings who would write questions and write answers, and they would train that, and that's called supervised fine-tuning of the ChatGPT. But that's with all these billions of parameters, you need humongous amount of human input to try to refine or align ChatGPT with only human data. So what they did, let me scroll this next paper. This is a figure from the paper. So the step one is the supervised fine-tuning with human data, where the human writes the response and then provides it, and then this is traditional supervised learning for the large language model. But this, what they realized at ChatGPT is it's going to be much cheaper is if we could fit, they call this reinforcement learning with human feedback. If we can take a bunch of example prompts and answers, multiple answers, and have a human called a labeler to rank these outputs or choose which one they like. So now we're getting the preference data, and then using that data, they use inverse reinforcement learning to learn a preference function over textual responses. Now think about that. What kind of utility function? It takes billions of parameters actually to describe human preferences. But then using that, they've got a kind of a cloned human being, and then step three, they can magnify that many times and play out that fitted human preferences to further train ChatGPT to be more aligned with human preferences using reinforcement learning. So that's kind of all frontier work, just showing you that this dynamic discrete choice stuff you're learning is really relevant, is really frontier, and the computer scientists and people in AI have made like tremendous contributions. So what I'm going to do now is hand it over to Enoch, who is, he's in marketing. He's a PhD student going to be on the job market from University of Washington. And I was very impressed with their paper. and it shows the close connections between the inverse reinforcement learning and the dynamic discrete choice model, and one that would scale to very large sizes. So I'll stop there, Enoch, and turn it over to you.
So, hi, thank you for the very generous introduction, John. So I'm Enoch, a PhD student at University of Washington. And so a few weeks ago, John emailed me, and he told us that he likes this paper, and he wanted us to present this work in this tutorial so that I can give you a good idea of how state-of-art machine learning methods, how state-of-art machine learning methods can be applied to dynamic discrete choice model. So hopefully I can give you a good idea of um, how large-scale problems can be solved while building towards our paper. So hopefully I can give you some ideas about that. So let me share a screen. And please bear me while I'm setting up. Okay, so this paper is a co-work. This is done with my coworker and advisor, Hema and Lalit. And the paper's name is an empirical risk minimization approach for offline inverse RL and dynamic discrete choice model. Okay. So throughout, we're gonna be first describing the motivation um, behind these large-scale problems, and then we're gonna be discussing, to be on the same page, what we mean by dynamic discrete choice models, and then we're gonna be discussing what we know about how to fundamentally how to solve these dynamic discrete choice models. And then we're going to be switching gears to the proposed one-shot gradient-based optimization approach. And then we're going to be converting it to the estimation problem, which leads to the main empirical risk minimization framework we propose. And then we're going to be discussing the algorithm of how to solve it, and then its global optimality. And then we'll finish this talk by um, providing you some simulation experiment results. So let's first motivate the large-scale problems related to these dynamic discrete choice models. So the example I use is Walmart Plus. So as you may or may not know, this is a service that's a competitor of the Amazon Prime, and it gives a free delivery service when you're subscribed. It's a $13 per month subscription, renewed monthly. So let's say each month subscribers decide whether to discontinue or continue this membership, and Walmart wants to find the whether to give or not give the coupon for the subscribers. So if the Walmart gives a subscriber a 50% discount coupon, that Walmart will lose some money now, but it will make more money in the future by not losing the customer. But if the Walmart gives a coupon, doesn't give the coupon now, then Walmart won't lose money now, but the probability of customer being churned will get increased. So as a researcher, if you have this Walmart data, then we'll see the monthly data of individual users, like page views, session duration, like cart addition, and so forth. Maybe only a few of them, like one or two, may work, but we don't know which one matters as a researcher. And the Walmart action at each month will be like whether to give or not give coupon. Right? So of course, we can directly infer the reward function from this data a little bit, but most of the parts of the utility related, the reward related ideas, characteristics will be hidden. So this is, so we can think that this is a canonical dynamic discrete choice model problem because given the data set of state action pairs, we are supposed to infer the reward function or utility function. And the goal is now infer this unknown utility function u. So the natural question is whether we can apply the existing dynamic discrete choice models. So are you good so far? If you're good, I'll continue. So to be on the same page, then let's discuss what we mean by dynamic discrete choice models. Okay. So throughout, I'm going to be discussing a single agent problem, which means we assume that all the entities in the data set is homogeneous. We will discuss the extension to the unobserved heterogeneity setup you learned in the previous talks in the end. But for now, let's assume that it's a single agent homogeneous problem. So given the offline data set D of state action pairs where ST is the state at T and AT is the action at T, let's say the data set D is collected from agent interaction with the Markov decision process where the state S denotes the state space, A denotes the finite action space, P is the transcendental kernel, nu 0 is the initial state distribution, beta is the discount factor, and there is the reward part, agent privately observes, and typically we assume that there are two parts of the rewards. One part is the deterministic part of the reward, modeled by R, which we want to infer and estimate, and there's a random part of the reward, which is typically modeled by EV1 or TE1 EV distribution, which we sometimes call the Gumbel distribution. So, and this reward form was pioneered by the Rust paper, famous Rust paper. And this is sometimes, it's often called to satisfy linear additivity and then conditional independence, right? Excuse me. So given this setup, given the initial states S0, sample from nu 0, we define the distribution of state action sequences using the P nu phi, and you use expectation associated with this measure as E nu 0 phi. And then now we can define the key ideas, key concepts we discuss from now on. So there is an optimal policy phi star, which is the argmax of the expected discounted sum of the rewards. And the value function is the maxima of the sum of discounted rewards. And then the Q function is, the value function is the sum of maxima of the expected discounted rewards from the state S. And then the Q function is again, the maxima starting from state and choosing an action A. And the relationship between V star value function and the Q function is that the Q function is the sum of R and then the discounted beta times expected value of the next state value function. Okay, this is everything we all know, right? So basically the setup of the dynamic discrete choice model is that given the assumption of rationality, which means that the agent should interact with the MDP following the optimal policy phi star, we can define the dynamic discrete choice model as finding the R hat, which is the closest to the true R in the sense of mean squared error, and the mean is the data distribution, which is sampled from the nu 0 phi star. Okay. So, and there is the concept of S bar I introduced here. This is simply means the reachable set by optimal policy. So it's called coverage. Okay. So are we good up so far? So good. So and there are basic results in dynamic discrete choice model, often called the optimality equations. I'll be using this concept over and over and again. And there are two optimality equations. And those, now what I mean by optimality equations is that the phi star and the q star must satisfy this equation. So the first equation is about phi star q star relationship, where phi star must satisfy that it should be the softmax of the q star. The second equation is famous Bellman equation, and the form we use is written in terms of the q star, which means that q star must be equal to r, the flow utility or the reward function from at this current time step, plus the discounted value of the respective value of log sum exponential of the q star for the next state, the next action. And there's a delta and gamma term, constant term here. So what you saw in the setup was that there is a reward random part, which is modeled by the Gumbel or the T1V distribution, which follows the G delta 1. And delta is the location parameter. And typically in the econometrics papers we use the G01 distribution, which makes non-mean zero distribution, and in this case mean is gamma. And if you use G minus gamma 1, then it becomes a mean zero distribution and the mean becomes 0. So effectively this constant term we saw here becomes 0. Okay. So for simplicity, throughout we'll use G minus gamma 1 that makes this constant term 0. But all the discussions we're going to be having from now on won't much matter about this choice. Okay. So John gave us a very nice introduction about the dynamic discrete choice, inverse arrow equivalence. And the only difference between the dynamic discrete choice model and inverse arrow is how you explain the randomness you observe, randomness in the action choice you observe from the data. So our community's explanation about the randomness is saying that, oh, okay, there is an unobserved random state component that induces this uncertainty. And whereas inverse RL's explanation is saying that agent has an inherent preference towards the random action choice due to some regularization that penalizes the deterministic action choice like that. And one nice fact is that, so we gave a brief proof about this fact in our paper appendix, is that exactly the same optimality equation we discussed earlier holds for both dynamic discrete choice and inverse arrow. So indeed, inverse arrow communities has been rediscovering what DDS has been developing, and all the contributions you make for the dynamic discrete choice can be rewritten in terms of the inverse arrow language and for the machine learning community. So for example, there are some recent papers, and there's a sixth one by Zhang, published in Europe's. This is actually a rediscovery of the Hodgson-Miller paper, actually. It goes like that. So then now they are now on the same page about what we mean by dynamic discrete choice models and the key ideas. We can discuss what do you know about how to solve these models, okay? So let's recall the optimality equations we discussed, and we would like to use them to find R and Q star. So for that, let's rewrite these equations a little bit, okay? So in this equation, we had phi star equals this softmax of Q star, right? So let's define this softmax of Q as P hat Q. Then for some arbitrary Q, to satisfy this optimality equation 1, it must satisfy phi star being equivalent to P hat Q, okay? So a nice lemma is that for the set of Qs that satisfy this relationship of phi star equal to P hat Q for the reachable sets is actually the set of Qs that minimizes the expected negative log likelihood. So this concept is very familiar to you, I guess, and we call it L and LL loss, or NLL loss, negative log likelihood loss. And so we can now rewrite the entire optimality equation 1 using this minimizer concept. Okay, are you good up to so far? So basically, there are many research, but all the research reduces to almost all the research reduces to the known results for solving these dynamic choice models. So given the assumption that we normalize the rewards for one action for each state to 0, this is called the identification assumption. And under this assumption, we know two ways of solving the DSE models. One is the Rust 1994 way, doing minimizing that expected negative log likelihood loss while satisfying this Bellman equation. And there's another way we call Hatcher-Miller way. So minimizing the same log likelihood, negative log likelihood, but in this case, using the transition function, assuming that we know or we can estimate the transition function, simulating the Q star function given the R by forced simulation or numerical integration of this expectation. Okay. So for these approaches, we basically observe two challenges we face in terms of extending it for the large-scale problems. So one is the nestiness of the optimization, which means that it's not one-shot optimization. And another is that for each cycle of this nested optimization, we suffer the curse of dimensionality. So let's discuss the nestiness first. So in both cases of these approaches, the thing is that we need to parameterize R to satisfy these equation 2s, okay? But then we need to solve the nested optimization because all the optimization is actually in terms of Q. So the equation 1 part is the outer loop, which is about the optimization within the Q space. And then the equation 2 part becomes the inner loop, which is about deriving Q from R. So we go back and forth in terms of in the nested optimization format. Okay. And within each cycle of this inner loop part, we actually suffer the curse of dimensionality because when you choose the Rust way, then we need to solve the Bellman equation. And solving the Bellman equation, it takes a huge computational complexity, which exponentially increases as the state dimension increases. And if you follow the Hatcher-Miller way, you need to estimate the transition function, and it takes a statistical complexity which exponentially increases as the dimension increases. So, for example, in the Walmart example we've seen, let's say the problem is quite simple. So let's say we have 20 variables, each of which has 10 attributes. Then what happens is that the state space size becomes 10 to the squared up to 20. And this is actually what a modern computer cannot deal with. So this simple problem easily becomes an intractable problem for the modern computers of the world. Okay. So you can then imagine that, okay, now you may want to employ some state-of-art machine learning methods, or often also called the non-parametric functional approximation methods, to address this curse of dimensionality. So there are two ways to solve this Bellman equation with a transition function knowledge. So one way is to use the fitted fixed point iteration. So John has these ideas in this discuss this in his excerpt in the review paper he introduced earlier. And this method is also studied by Adosmuli and Eckhart, John also mentioned, to appear in the RES. And I'll explain this in the next page, but this suffers instability when combined with the neural networks. Okay, so another way of doing this is to employ the gradient-based squared Bellman error minimization. There's no prior works on this. People may have some sayings about this. I'll explain about this later. And this paper discussed this approach. Okay. So I said there is an issue with the 50-fixed point iteration in terms of instability. So what I mean by this issue is as follows. So it's a very famous result by Chiklis and Roy, big people in the offline reinforcement learning. They say fitted fixed probability methods can diverge even when all the very, very nice conditions holds, which are all in realistic. So you have infinite data, D is infinite, and the fitting is exact, so that you use infinite computation for the perfect optimization. And the true, the real function form is linear, and it's even the one-dimensional linear function. And then with this all very nice conditions, you still suffer divergence in terms of the convergence. So fitting actually, in most cases, cannot ensure convergence. And this is not just a theoretical phenomenon of and this is quite a huge issue in practice. And this issue even becomes worse when you combine with the neural networks. So why this happen? So intuitively, for the people who know some ideas about offline RL or RL, for example, Q-learning, what you do is that you basically solve the optimal equations by bootstrapping the current candidate you're thinking of, right? Current candidate, the value function you're thinking of, right? And those value functions are non-existent hypothetical functions. You use it, but you bootstrap on top of it, right? And the key idea is that if you do that, then that causes a huge issue. And that huge issue becomes even worse when you're using the neural networks. So the question answered in this paper is whether we can develop a scalable gradient-based method that can infer reward or Q function while probably ensuring the global optimality without any assumption on reward structure or transition function knowledge. So let's now jump into the what you're trying to do. So which is the one-shot gradient-based optimization approach. Okay. But also up to so far, is there any questions? Maybe I should watch Julep for that. Okay, so if there's no question, I'll move on. So for the discussion, I'll introduce some terms. I'll be a little bit slow. It's mouthful. So let's define a Bellman operator script T or T as TQ and T, where TQ means that it's being equivalent to RSA plus the beta expected value of the logarithmic exponential of the Q of the next state. So this is the right-hand side of the Bellman equation. And define the empirical Bellman operator T hat as this expectation removed version of this Bellman operator. So this is what you actually see in the data set, okay? So, and note that expectation of the T hat Q is TQ, okay? So please stare at this for a while, and I'll move on. So the Bellman equation then can be written, as I told you, as Q star being equal to T Q star, okay? And this is what the true Q star should satisfy, okay? So if you want to claim that the Q you found is close enough to the Q star, then we should test that this difference between Q and then TQ is small. So we define this Q minus TQ square term as the squared by Bellman loss and call it LBE. And for the TD term, with using this T hat Q as the squared temporal difference loss, and we call it LTDQ, okay? So let's go back to the Rust way of doing this. So we saw that with these two optimality equations, we can identify this R and Q star. And this is saying that the second optimality equation is about satisfying the Bellman equation for all these stated actions reachable by the optimal policy, right? And now there's a famous result by Magna and Sesmar showing that we don't have to satisfy Bellman equation for all the set and actions. When we have this first optimality equation, we only need the Bellman equation to hold for only the SAS pairs, where again, AS is the normalized the rewards for each actions, normalized rewards for the chosen actions for each states. Okay. So one nice thing is that we can rewrite this second condition also in terms of minimization concept. So you can rewrite this as the Bellman loss, squared Bellman loss being 0 for this AS terms. And then you can rewrite that this Q functions that satisfy this Bellman equation is being equivalent to the minimizers of the expected value of this indicator function that says we only cover the data that satisfies that action is this anchor action or this AS action times this LBE, okay? So now the modified form of this identification becomes the combination of the two minimizing equations, where the first one of the was the about L and L loss, negative log likelihood loss, and the second one was about minimizing the square Bellman loss constrained to the this A equal AS data. Okay, So, and you can see that for this negative log likelihood loss, this was about the softmax of Q. So this doesn't have the R-related term. And what's nice is that in this term, because we are focusing on only on the data, which satisfy this A equal AS, where we exactly know what the reward is for these pairs. So there's no unknown R thanks to assumption 2. So which means we don't need R parameterization anymore. And so if we parameterize by Q, then we can avoid the nested optimization altogether. Okay. So far, so good. Do you understand what I'm saying here? Okay. Perfect. So the one-shot minimization we are proposing here is very simple. So we saw that with these two terms, and we are minimizing these two terms, so we can just simply combine these two terms and minimize it. So we call this objective as expected risk, and expected risk minimization problem is defined as minimizing this expected risk. And as you can expect, we can show that if you minimize this expected risk, then you can identify the true Q star up to this covered states and actions. And furthermore, you can identify the R by the Bellman equation. Okay, so this is very straightforward. But the thing is that converting this idea to the actual estimation takes some challenge. So I'll discuss that part. So the idea of estimating this expected risk concept looks straightforward, but it's actually challenging due to the fact that we have this LB term here, and then LB term again includes this TQ. And TQ, the right-hand side of the Bellman equation, it includes this expectation part. And which means we cannot empirically just know this, compute this without knowing the transition function. So what it can instead estimate is the T hat Q, which is the expectation removed version of this, where we use the observed as prime instead of the expected stuff. Okay, so you can say, okay, then a natural proxy for this Bellman error here, TQ minus Q star, TQ minus Q squared is expectation of the TD error, which is DT hat Q minus Q squared. Okay, and doing this is often called temporal difference method. And the question becomes whether this works. And unfortunately, minimizing this causes a serious issue. So the issue is that TD method, minimizing this left-hand side equation, does not guarantee that the Bellman equation to hold, which means the Bellman error becomes 0. Because there is a bias term which never goes to 0 with the infinite data unless the transition P is deterministic. And this term is written as TQ minus T hat Q, an expected value of it. And this is effectively the variance of T hat Q, right? So due to this transition to S prime. So you can say that if transition to S prime is not deterministic, then the variance is not 0. And this term is Q-dependent term, which means that if you minimize this entire TD term with respect to Q, then you're not just minimizing this Bellman error term, you're minimizing this entire term, which causes bias. Okay. So for the same reason, so there is a gradient-based method proposed by Adusmuli and Eckhardt, which is called the semi-grand TD method. They show that their objective is minimized, but minimizing their objective, which is TD objective, does not guarantee that the Bellman equation is whole. The Bellman equation holds. Okay, which means that this B term is minimized. Okay. So why does it happen? Let's define delta Q as T hat Q minus Q. And intuitively, bias above happens because what we are trying to minimize is the right-hand term, which is the square of expectation of the delta. So delta is taken the expectation and then getting squared, whereas the TD term, which is the left-hand side, is the squared and then taking the expectation. Okay, so effectively, to avoid this issue, you want the expectation and the squared to be commutable, which is not. So this issue happens. So this square term is problematic. So to avoid this issue, we can employ the technique called biconjugate trick, which replaces the problematic square function by maximization problem form of the linear function called biconjugate. So this is a mathematical fact that the square function can be converted to maximization of the linear term. So this E of expectation squared is now 2 times expectation times H minus H squared, and we are maximizing it. So the solution to this maximization problem is equal to this original square. Okay, so you can see that for this expectation now, there's no problematic square, and because we can freely reparameterize H and optimize something else, we parameterize H by this zeta term. By some massaging and some surface from algebra, we arrive at some intuitive equation, which is quite mindful. I'll be like covering this one by one. Okay, so lemma 5 says that we can express this squared Bellman term, which is TQ minus Q squared, as TD term minus B squared of times DQ term. And this DQ term is effectively, so given the new notation of BQ with log sum exponential of the Q we are considering, this DQ term is actually just the variance of VQ due to the transition P. Okay, so given that we know we are at the state S and action A, what's the variance of the value function of the next state, like that. Okay, so and this is the reason for this is that this is the minimization equation, and you can see that we are minimizing the VQS prime minus zeta squared. This is effectively the mean squared error minimization problem we often see, and we all know that the solution to the mean squared error minimization is the expected value of the V, right? So this is EV you see opted, right? So, and then knowing this, we can define the minimizer dq as this zeta star, and which is the max minima of this objective, the optimization equation. And as I said, this is effectively EV, or expected value of the V star, when we are talking about the Q star. So after solving this optimization problem, we get this zeta star, and then you can use zeta star to compute the R given the Q star, okay? So using this, we can rewrite the one-shot minimization expressed by the expected risk minimization framework, which was this to be the sum of negative log likelihood loss term plus this indication function of TD term minus this the value function variance term. So you can rewrite this as this blue term, another term. This is the TD term, and then this is the variance of the V term, okay? So, and then, as I said, because V star, the zeta star we get after all the optimization effectively becomes the EV. You can subtract this EV from Q star and get the R. So previously we saw that if we started from the R parameterization and derived Q star, it was problematic. Here, we are doing all the optimization by Q star. And what's really nice about this is that the R estimation after the Q estimation is actually free. Okay. Are we good so far? Okay, perfect. So now then we're ready to convert this expectation related identification result into this sum and 1/n related this estimation equation. So we are just simply replacing this expectation into 1/n and sum of the data. And we call this form the empirical risk. And the optimization we need to solve this whole Q-star finding problem becomes the minimization problem of this empirical risk, okay? So if everything is clear, I'll move on. So, but we are not yet there to discuss what's the actual algorithm to minimize this objective. So I'll discuss that part now. So let's just do the typical parameterization thing. So let's say we parameterize our cube function using, for example, linear, polynomial, or DM neural networks, and call it like zeta. So let's say q zeta is the parameterized form of the cube function. And we make the following assumption, often called the realizability assumption, saying that the class of functions we consider actually includes the actual Q star. So there exists the zeta star where the Q of zeta star is exactly equivalent to the Q star. Okay, so if your function class is expressive enough, then it's likely to hold. Okay. And as we discussed, we would like to solve the minimax optimization problem of this form, where we had this minimization of the Q, and inside there is a minimization of the zeta part. So this is effectively minimax because we are subtracting the minimizer. So this is mini-max, right? And the canonical way of solving this minimax optimization is to apply the gradient ascent descent, where we initialize the arbitrarily zeta and q, and we alternate between maximizing for zeta and minimizing for q. Okay? So what you're doing is basically this. We initialize Q and zeta, and we draw batches of B1 and B2. You can just use the full data set, but it's just making it more realistic. Our proof about these batches extend to the full data set part. But what you do is that given these batches, we take the ascent step of solving the mean square error, minimizing the mean square error related to the zeta. So we minimize this equation to estimate the EV, which is zeta. And then given the Q we know, okay? And then after this step, we use this estimated zeta to compute the negative log likelihood loss and the Bellman error loss and minimize it, fixing this zeta and updating this Q. Okay, and so we iterate between this zeta optimization and the Q optimization back and forth like that. It's a kind of squiggly like gradient ascending descent like that. Okay, and then when it converges, you use this final zeta and Q to derive this actual R. Okay. So you may wonder whether this will indeed converge to the global optima. And to say this, we need the concept of Polyak-Ryashevich condition. So a function f is said to satisfy the Polyak-Ryashevich condition if the solution set is non-empty and the minima is finite, and then there's just a constant c, so that when the G and the G theta and G theta star, which means the suboptimality of current theta is not zero, then the gradient at the current theta is positive and actually is proportional to the suboptimality you observe. Okay, so it effectively means that if you're suboptimal, then your gradient is never zero, and its size is guaranteed proportional to the suboptimality you currently have. Okay, and you may not have an intuitive idea of how this function look like. So this is strongly convex function. This is convex function, and this PL function is it's kind of non-convex function, but you can see that if you take the gradient descent, then it'll go to the global optimal fast. And it's known that the rate of convergence to the global optima is actually the same as the strongly convex case. So it maintains all the convergence properties of the strongly convex function. Okay. So ideally, for this minimax optimization, it's known that if the function we are solving the minimax optimization satisfies this PL condition in both sides, then it's guaranteed to converge the global optima through gradient ascent descent, which is what we did in our algorithm, right? So the query is that if the if this full equation we are minimizing satisfies the PL condition with both theta 1, which is related to zeta, and theta 2, which is related to Q, satisfies PL, then the Gladius algorithm we've proposed will achieve global optimality. Okay. So what remains is whether this our objective really satisfy the PL condition. And what I show in the paper is that I define some assumption, and that I show that assumption is not very strong to satisfy, not too strong, that the linear function and the neural network parameterization satisfy that assumption, And what I show is that under that assumption, this negative log likelihood loss and then this scared Bellman loss satisfy the Pillar condition with respect to theta. And you can extend this result to showing that indeed for the same parameterizations, expected risk and the empirical risk, while you're minimizing, both satisfy the Pillar condition. And then the corollary and the final theorem is that the Gladius algorithm achieves global optimality, which means that it effectively finds the true Q star and true R for the linear function class and vector function class, like that. And what's also really nice is that you can use this Pillar condition to say something nice about the statistical complexity. So there's a known result then that if you're given a n sample data set, then minimizer of the empirical risk, which is this theta star, dn, the mean difference between this theta star dn and the true theta star can be bounded by 1/n rate. And this is a finite sample rate, which means that it's not asymptotical rate, which is good. So this theta is specified in the paper. So to summarize, the final theoretical form of this outcome of this Gladius is that under the realizability assumption, saying that the function class is expressive enough to include the true Q star, with the parameterizations we consider this Gladius algorithm's result, the mean squared error between this and the true theta star is bounded by 1/t error and the 1/n error, where t is the number of gradient steps and n is the sample size. And again, this is the finite sample and finite computation bound, which means that we can actually specify these constants. It's not a asymptotic bound. So, and this is scared, so which means that this is effectively O of 1/n squared, 1 divided square the root of t, and O of 1 divided by root of n rate convergence, which is par existing parametric methods. Okay. So now let's move on to discussing how good this proposed algorithm is in term simulation. Okay. So we conduct our simulation using everyone's beloved Johor a bus engine example by Rust 19887. This in the problem we discussed the bus coming to the maintenance station, and we decide whether to replace or do the maintenance of the engine, and the replacement cost is proportional to the mileage. So if you replace the engine, then you pay some say some cost proportional to the mileage. This is reversed. So maintenance cost is proportional to the mileage, and the replacement cost is the fixed cost of C2. Okay, sorry about the mix up. So basically, when the bus returns, mileage randomly increases, and when you replace it, then mileage is reset to 0. And when you do the maintenance, then mileage is stayed at the same rate, like that. So there are baselines we consider. There are oracle baselines. We call it oracle because we assume that the true parameterization form is known, and we also give the model the exact transition probabilities. And we also compare with the method by Amazon guys for the large-scale problems. This is about combining Q-parameterization and the TD method. And these are popular RL algorithms. And this MLRL is actually what I discussed earlier. This is actually effectively the CCP approach, except that they explicitly consider some the first stage robustness uncertainty stuff. Okay, and the um, the measure we use for comparison is mean absolute percentage error, which means that we are dividing the error in the estimated reward by the actual reward, and we take a mean and then take the percentage of it. Okay, and we tested for many size of the problems. One trajectory is 100 transitions, so 50 trajectory means that it's 50 trajectory of 100 lengths of horizon problem, so it's effectively 5,000 transitions like that. And we can see that our method is much better than non-parametric transition with no knowledge of transition probability methods. And actually, this MQ doesn't scale given their algorithm. And then what's really surprising is that, and then counterintuitive is that our method actually does even better than this Oracle baselines where they know the exact transition probabilities and also they know the exact parametric forms. And it's counterintuitive, and you may want to know why this happens. So first of all, it's not that ours is good, it's just that Gladius does well only in the frequently occurring regions. So because our measurement is over the data set, if you do well in the frequently occurring regions, then it's fine. But our Gladius algorithm does bad when the mileage is actually not too much altered. So for example, in this bus engine example simulation, we can see that from the mileage of 6 to 10, we don't really observe like any data, and we are completely extrapolating. And for those regions, Gladius does very poor, but you can extrapolate well for the SISP and Rust like that. So, but still, you may also wonder the reason why this Gladius does better than this parametric methods for these regions where data is well seen. Okay, and this is also a known result. This shows something we know about estimate difficulty under data imbalance. So in the RL, it's known that the use of a projection operator onto the space of function approximators, and functional approximators means it's a way of extrapolating, right? And doing this with respect to the distribution induced by a behavioral policy that can result in poor performance if that distribution does not sufficiently cover this state space. Okay, so if your approximator is with a very small model, which, so for example, linear model, which extrapolates a lot to the data poor regions, then this projection operator stuff goes bad. Okay, so which is effectively the case for this problem because in this problem, all trajectories start from mileage 1, and the replacement action 0 resets the mileage to 1. So most states observed in the expert data or the 5 star are within the mileage 1 to 5. Okay, so this is what happens in this particular simulation. Okay, we also provide the scalability test because the whole point of this this research about whether to check whether we can apply dynamic discrete choice model for large-scale problems. So as we saw in the Walmart plus case, we see a similar problem where we have many attributes, bus mileage, bus age, downtime, customer complaints, but actually what only matters is the bus mileage. But as a researcher, we don't know that only bus mileage knows. So we have this bunch of dummy variables given. And we would like the algorithm to identify the fact that only the bus mileage matters. Okay. So we tested this from the dummy variables from 2 to 100, which means that these dummy variables are like 100 variables. And and then also for each variables, we used 10 attributes, which means that the size of the state space becomes 10 to the 100, which is like larger than the number of atoms in the universe. And we saw that our algorithm's performance degrades a bit by 10%. This is 1% to the 10%. But still, we only loses like 10%, which is not very bad. Okay. So the summary is that we want a scalable dynamic discrete choice method. And the question is whether we can combine this with the non-parametric machine learning methods. Okay. So the fitted fixed point iteration methods are probably unstable. And there's no globally optimal convergent gradient-based method exists because previously people didn't know how to minimize the Bellman error related terms effectively. But we in this paper show that this Bellman error related term has PL conditions, so we can just minimize it. Okay. So in the study, we propose one gradient-based method, which is called the empirical risk minimization framework, and which is global optimally convergent, even with the neural network parameterization, and which has a nice empirical performance for the standard benchmark. And it scales well up to 10 to the square of 100 states, which is larger than number of atoms in the universe, losing only 10% precision like that. So, and there are some further discussions. I have some time, so I'll just go over it briefly. So one question you can make is, how is it possible to identify the rewards if the data size is like far smaller than 10 to the 100 state? So think of it like fitting a smooth sheet to the few measure point on the landscape. Once you know how the sheet bends, you can read off the height anywhere without having measured at every spot. So the sheet is controlled by only a few thousand adjustable knobs, which is in our case neural network weights, and the sample size we need depends on the knob structure complexity. Okay, and another question you can ask is that, okay, so I understand that you can estimate R and Q star, but for the counterfactual estimation, you need the explicit estimation of P, and you cannot just avoid the estimation of P altogether, which nullifies the whole sense of this purpose of the whole sense of this research. The answer is no. Given the data set state action, state action, state actions, and pairs. If you know the R hat, then we now have state action R hat, state action R hat, and given a counterfactual scenario, for example, a reward intervention, then we can apply the offline reinforcement learning algorithm directly without transitional probabilities estimation to recover the corresponding counterfactual optimal policy. Okay, so those are the discussions, and there are immediate extensions of this research. So I discussed earlier that all the discussions we gave was effectively about the single agent homogeneous case, and this method can be extended to address unobserved heterogeneity. And so this adapting to unobserved heterogeneity is often called the in-context learning in machine learning. And we can implement actually this in-context learning given gradient-based estimation method. And the thing was that actually, when I was starting this research, I didn't try to develop a gradient-based dynamic choice method. We just wanted to develop a in-context learning method for the dynamic discrete choice model. And we looked into the literature and we couldn't find a gradient-based method. So that's why we developed one here. So our working paper is coming out soon about this. And another extension is that this PL condition proof we gave in this paper can be extended for offline reinforcement learning. So also in the offline reinforcement learning, there's no gradient-based offline RM methods because people yet don't know how to deal with this Weimaraner term well. So the results in this paper can be easily extended for this kind of approaches. So another working paper is coming soon with that. So thank you for listening. A special thanks for John for the kind invitation to give this talk and for the detailed and insightful comments on the paper. And many thanks to as well to the organizers. And thank you very much. Okay. So if there's any questions I can answer, we have around like 5 minutes or so.
Is anyone there? Did they all pass out due to the heat?
Yeah, we're still here. We're still here.
Yeah, I know it was a long day.
A little bit overwhelmed.
I have one question.
Oh, sure.
You have this assumption called realizability, which
Oh,
means
yes.
your neural network is going to exactly capture the true Q, right?
Yes, yes.
That's a convenient. If you didn't know what the Q was, then you could extend this and you'd use a sieve, right? You'd start with a small parameterization of the neural net and then gradually increase it. And so that you could use sieve methods in econometrics. Have you considered that or seen other work that uses sieve methods so that you don't have to assume that you know that your parameterization includes the true Q?
Yeah, right. So what I understand about the sieve methods is about polynomial like way of doing approximating the functions, right? So you can definitely do it. And the proof for the linear case actually extends to that case. So it's you can think of it as just a hyperparameter tuning problem. So your problem may be too complex to be solved by polynomial approximation or not. So you may start from using sieve, and in large problems, then like with like 100 variables with like very complex like functions, polynomials may not work. So in that case, you can check that, okay, sieve does not work, then why not using the network like that? So yeah, you can, I think, definitely use sieve instead of neural networks. It's just the about trying and then checking whether something works or not, like that.
Just the one follow-up question. So in the
Mhm.
bust problem, without the extra irrelevant state variables, how deep was your neural net? Was it a one-layer neural net? Could you get by with just a single layer neural net to approximate the Q function?
Oh, great question. So I didn't include it in the image, but it was a two-layer neural network with 10 widths. So perceptrons in each layer was 10, and it was two layers. So the parameter size was around 100, like that.
100, okay.
It was very small neural network. Yeah.
Yeah, but then when you went and you added all these other 10 to the 100th extra variables, how big was the neural net in that case?
So this problem is a very small problem where we a priori know that it's very like the true real function was linear, right? So in this case, two layer was sufficient. So my choice of the very small neural network was actually attributed to knowing the fact that it's actually the true the reward was quite like simple, but in the real world case, you may face a situation where the the true rewards function is much more complex than this linear, and then definitely you may should consider using the larger neural network. But actually, the thing is that the cost you pay for using the larger neural network is quite small in nowadays computational powers. So all you pay is the memory, and then you can now run like extremely large. For example, you can even run the language model size neural networks in your local computer with like very cheap GPU with $200 once. So you can definitely start from large if you want, like that.
Okay, thank you. I'll shut up now. But thanks so much, Enoch. I very nice presentation. I really and very impressive results you have.
Thank you very much.